They are putting two side by side to illustrate what was the wrong. They had some indications. It did not meet its targeted velocities during the liftoff. So they didn't know that it is something wrong, and they didn't know exactly where it was wrong. So they tried to overcome that, and they could not do it. That place, due to that one of the during liftoff, that place it got burnt. That place, that foam got sheared off.
Guidance now converging Columbia's onboard computers commanding the main engine nozzle to gently swivel, aiming the shuttle for a precise target in space for main engine cutoff. Columbia now 43 miles downrange, 35 miles in altitude, traveling 3,200 miles an hour with propulsion altitude.
That's so then it disintegrated after 16 minutes. That because of that thermal shielding becoming weak actually. They did calculate also, but still they could not. This another say this is one of the missiles which failed to one structural member not being designed properly. Right. Again, just goes again in design. Okay. So to yes, so to overcome these kind of design failures, we do something called say different environmental testing. As I mentioned in the before, there can be a dynamic testing or say climatic testings. These testings, all of them put together, will bring out all the failures that may happen in the actual operation. Yes, even after doing this, they also have done all these failures, but still there are going to be some failures. So, doing this test, we should take very corrective steps so that we avoid failures in the actual environment. So, right now I will focus on vibration testing. Why we do vibration testing? See, vibration testing we do just for two things. One is to check the structural integrity. Like the last missile, when we checked that missile failed due to one of the structure being not having the same strength as the coupler. So such situations we can avoid before by doing this vibration testing. Second is we need to check whether these electronic systems are they functioning as per their intended specifications during these environments. So we have to simulate the correct environment and see the functionality of the electronic systems. These are the two major things that we check during vibration. So there can be different types of testing methodologies. Like for example, during development testing, we will do one kind of input. Due to qualification means this is a high level testing, we will do one type. Acceptance is one type. Like what we mean by development testing is, in the initial stages, it is to identify the problems in early design stage so that corrective actions can be taken. In this what we do, we give more levels than the standard what specifies. So that any failure is there, we correct it and then go for redesign. Qualification testing is kind of test that will evaluate after the design is frozen to demonstrate that whatever design has been frozen, adequate margins are there in the final product. Acceptance test is like a production test. Means once you are done all your testings, everything, your design, frozen your design. Now you have produced items in bulk quantities. Now you have to know whether all these produced quantities are meeting your specifications. So that time we will do one-to-one. Every item in the produced line will be tested, but not for the levels that have been in the design stage, but at a lesser levels, just to check that yes, everything is okay, the process is okay, the manufacturing techniques are okay, workmanship is okay. So these are the differences. Now, when we say testings, anything we need to follow some standards. Yes, we also follow. These are the standards that we follow. It is either MIL standard 810, it is from US Air Force and Navy. So these are all called environmental engineering considerations and laboratory tests. These are consolidated field data from a large number of flight tests of different types of missiles. It started with 810C and latest version is 810D 2008, September 2008. Now for our instead of taking from military, our own people, defense people also have made standards, the giant service specifications 0 to 56 or JSS 5x5, Phantom 5 we call. These are for basically environmental test conditions of missile systems. We follow this. In any case, whenever required, we also follow this. So all our missiles will be qualified against these two standards. Now, when we want to test in laboratory, we need to simulate. So we will need some equipment that is required. So what are the things that we need? So we need basically to simulate vibration, we need three things. One is the vibrator or we call shaker, and then power amplifier, controller, accelerometer, vibration test specification. Let me show you the diagram. See, what we do is, this is what we call a shaker. The shaker works on some principle called Fleming's left-hand rule. I will explain in detail. Basically, Fleming's left-hand rule says that any current carrying conductor placed in a magnetic field, you generate a force perpendicular to the magnetic field and current. So, suppose this fellow is giving particular force with some designated rating. You have an item, that is the unit aerospace unit that is to be tested against a particular level given by some standard, suppose. So this unit is like, say, any one of the unit like this. Now we will give input. We will put something called responses at some locations where we need to read what is the level coming. So that is processed and then through some called data acquisition system and processed and then found out. Also we need to give the input, so we use something called control. It is like a one which gives a digitized data. This data is amplified by something called power amplifier, so that the voltage and current as required by the shaker or demanded by the shaker are met. And this being a closed loop, it follows for every say milliseconds of operations depending on the range that we choose. Now in the closed loop, we strictly monitor that level that we need to give on input are going, and also the responses are monitored at critical locations. So what is our role is that we need to control the input. You need to identify the locations where you need to put. You do a low level, like let's say full level. When we say low level, what we mean is you initially give a low input and see the response, so that if there is any problem, you correct it and then give it. And then analyze all these responses. And if there is any problem in the responses, then you need to modify the structure. Actually, accordingly design, change the structure, and then try to see reducing the input, so that your systems are protected. So I will explain one by one component of all the. First one is the electrodynamic shaker, means that is this component which sits here actually. This, as I told you, works on Fleming's left hand rule. That it has a magnetic field inside and a current carrying conductor. So due to these two, you get a force perpendicular to these two quantities. So the force is given by some formula like this. Now, once the shaker is there, we need to, the amplifier requires this to the shaker to give this magnetic the power to the magnetic field and also the current. That means, sorry, that means we need to send a lot of power. This magnetic field is generated by electromagnetic field. So we need some kind of DC power, voltage or current, and this current is AC. So alternating current, it needs voltage and current. Now there are different types of shakers that are there. See, it started from the mechanical shakers to now what we use called electrodynamic shakers. Depending on the range that we need and the signal that we need to generate, there are different types of shakers. We choose these electrodynamic shakers because of our frequency range being this here, and all our shakers are electrodynamic. And now the next one is the amplifier. What does it mean is it amplifies the input voltage and current and sent to the shaker. It is like a muzzle puller. It provides the power. Now controller. There is one digital controller in the loop which gives the input on the shaker end. So what it does is, suppose you want to generate this kind of profile, but structure will have its own frequency, something like this. Now this fellow has to understand this signal and invert this so that you get on the shaker and this like this flat profile. So controller is basically, it has to account for all the structural resonances in the circuit. So then we answer this not important. And we have generated our own controllers. This algorithm inside the controllers, how it does. So this is not important. And you need a lot of instrumentation to do these things. Like say you may need accelerometers, sensors. You may need charge amplifiers, data analyzers for doing all this. But these are all instrumentation. I will explain it. These I will explain. Now let us see what are the vibrations we do. We do something called sine vibration, something called random vibration. In sine, what we mean is only one frequency is exciting. You can see in random here, both are excited at the same time. For example, if I take one component where say this one having one frequency 22, this has 33. If I excite sine, means only this fellow will excite either 22 or 33 at a time, depending on the frequency I give. What we do is random because the environment that we get in missile is random. Means all the frequencies in the 5 to 2000 Hz, all of them are excited at the same time. That's why I have shown a demo where when we do random vibration, both are oscillating at the same time. So this is more dangerous to us. This is observed in some rotating components. For example, if it is a helicopter vibration, you will get sine vibration over random vibration. But for our missile application, it is a random vibration. Means we get all the frequencies right from the beginning. Yes, I have shown you the working principle of electrodynamic shaker. Let me show the full shaker how it looks. If you see the cross section, it's something like this. This yellow one, what I have shown is a, like say conductor. It is placed in a magnetic circuit. This blue is the magnetic circuit, you can assume, or we call it the body. When it is put in this narrow zone between the center pole and the outer body, you generate the flux at this below using this green things called electric or say field coils. So this field coil will come here and cut here in this narrow zone from here like this and here like this. So in this narrow zone you have a magnetic field, and this being a current carrying conductor, you have a magnetic field and current, and then due to these two you get a force as demonstrated here, field and this. So you get according to this. For example, see armature can look like this, the field coil can look like this, and this core here, this is like this, and this can be a body. So it is like this, and see how we test for a few suspense I will show you. So this is like some kind of fixture, this is the shaker, and this is a missile. So we fix it to the shaker, we generate at the required base, and we take along this missile number of responses where we want to see what is the response coming, and whatever we may need other mechanical aspects. I have shown you data acquisition, instrumentation, but we apart from that we may need some kind of fixtures, what we call say head expander, because of this size of the equipment being more than the size of the shaker. So some kind of road support platforms, we call slip tables. These are all the mechanical aspects that may require you to test. See for example, see I have some missiles which are say 2 meters, some kind of missiles are say 2 meters dia, 3 meters dia, we here. So then how do I test it? I may have a shaker of say 500 mm, 600 mm. So then I need to have some kind of say this called head expander, means expanding the head, so that top you have 3 meters, bottom you have 2 meters, but this should have a frequency range so that I can operate my system up to 2000. So this fixture should be designed for 2000. Likewise, I may have some kind of slip table where slip table means when the shaker is oriented in other direction, you have some what we call it as slip table. So this kind of, then we may have some requirement where the load on this shaker is say 2000 kg, 3000 kg like that. In that case, we need to have some kind of load support platform which can take the load but still not harming the shaker, but we are able to do the test. So these kind of things will be there. Some of the sections we are showing here. See how it can be mounted, how it can be tested. See, these are some Astra missiles, suppose they are tested on some kind of shaker like this. Some shakers can be tested in vertical motion like this, depending on the axis. Every missile that we do, as a subsystem or section of the missile we will do it in 3 axes. In the sense, one longitudinal means vertical and 2 lateral, what we call. So this can be say one of the axis called vertical axis. This is vertical axis. This can be you can see in lateral axis. This is the whole one of the missile we have put, and then we are trying to test it. And these are the different systems and subsystems what we are showing you different pictures. And what we do basically in all of this is, like I have told you, we input at the base of the system some kind of spectrum like this, what we call a random vibration spectrum, where the y-axis is in terms of G square per Hz, x-axis in frequency. It is similar to like G versus frequency. Because it is a random, we need to give in consistent units called G square per Hz. This is power spectral density we call. So when we give this kind of input at the base, there are some critical elements or say critical subsystems inside, means packages. At all packages we mount some kind of sensors called as accelerometers, and we take the feedback, means for this input how the subsystems are responding. See, we have some kind of response like this. If this response is harming this subsystem, we have to modify the structure or the interfaces and rework. If it is not harming, then we will go ahead with this. So by reading this information of the response, we will know where it is amplified, where are it is fine or it can withstand the vibration, and what are the effects, what are the total acceleration input that is going at the corresponding packages. Like these all information we read from the responses, and if required we do some structural modification. I will show you some of the structural modifications we have done as a case study. I will show you. You see, this is one of the Agni missile when we test it, how it looks. All that. To have you some idea about the test specifications, some of the test specifications say different, like the Agni series will have some 20 to 2000 Hz. The test specification maybe 10 minutes, and what is the input level we call 0.02 G/s. If it is say Akash, it will be like 1 minute test, but very high level. It depends. This test duration will depend on the flight duration of the mission. Some can be say 30 minutes due to if you want to see the endurance test, what we call. These are different these things. Right. We will show you some of the case studies what we have done in vibration science. See, we have, as a part of indigenous development, we have developed some kind of shakers. As I have mentioned before, shakers are like two types. When we call electrodynamic shakers, they are either air cooled type or water cooled type. In air cooled, what we mean is the heat that is produced inside due to the field coils are cooled by air. If it is water is used for cooling, then it is called water cooled. So, what are the critical components in shaker is like this? We will call armature, field coil, fixture, and body. Armature means this conductor which carries current, and it is required to be designed for above 2000 because of its operation range. So we have designed it to have a 3000 Hz frequency, and we realized also we made hardware. Similarly, field coils are required to give a magnetic flux density in the narrow gap around 1.5 Tesla. So accordingly we have studied and then designed. Then you need the magnetic body, or say the pole we call, center pole and the outer pole. That has to be designed. Then it needs to be guided. This conductor needs to be guided by something called flexures, which allow motion in the direction of motion in the vertical, but restrain in other two, means it should have a lateral stiffness more and the axial stiffness less. So it should be designed in such way. So we did design as per these specifications. Yes, we did test it and it is also good. We don't show that. Okay, apart from the air cooled shaker, we also developed the photon water cooled shaker to demonstrate the technology. The same concept here also, except that it is water cooled. Water cooled here means that armature water is flowing in the same hollow conductor, and the same current is also flowing. That is the criticality. Here, what happens? Here what happens? The conductor, whatever we used for this, is a solid conductor.